All right, so we talk about many hash functions, but we realized that the well-known like MD4, MD5, and SHA1 is broken. So we have SHA2, but only it remained. So, and it was very similar to the previous designs which were broken. So this was actually important time to decide if we needed another hash function or not, because if SHA2 is also broken, if somebody breaks SHA2, then we would lose almost every security in many cryptographic algorithms that use SHA2 or any hash function. So for this reason, NIST wanted to have a backup plan. So they announced a competition, a hash competition called SHA3, and it was held between 2007 and 2012. And idea was to have another algorithm which has the similar specifications like SHA2, which have the same message digest length and so on. So this way, people will be able to change from SHA2 to SHA3 when it is necessary, when SHA2 is broken. Okay. So the competition received 64 submissions. 4 of them had Turkish designers. And unlike previous competitions, NIST allowed designers to tweak their algorithms after round 2, so you could do some small modifications. There's a very nice web page dedicated to this competition called SHA3 Zoo. You can visit the web page, see every 64 candidate, all of the attacks and what happened to them after what round and so on. So the winner was Ketchak. Now it is called SHA3. And there were other finalists, Blake, Grost, JH, and Skane. Round 2 eliminees were the following: Blue Midnight Wish, Küpeş, Echo, Fugue, Hamsi, Lufa, Shabal, SHA3, and SIMD. I'm telling all of this because we will see them in the following slides again. But eliminees before round 2 were these. There were a lot of algorithms. They couldn't make it to the next round. Okay. So why these algorithms are important? Because they are used in mining puzzles of alternative currencies. So some cryptocurrencies use multiple hash functions for their hash puzzles. This complexity is expected to prevent efficient ASIC development. So recall what we did in Bitcoin. We calculated SHA-256 twice and expected to have an output value less than some fixed value for that block, right? So if you implement SHA-256 in a very fast way on a dedicated hardware, this means that you can mine faster. But alternative cryptocurrency designers wanted to allow their miners to use GPUs, not dedicated hardware. So in order to prevent building a dedicated hardware, they thought that instead of using a single algorithm like SHA-256, let's use many algorithms. So in this scenario, instead of using SHA-256 device, you actually use 11 different algorithms consecutively. So in the algorithm called X11, you are actually using 11 algorithms: Blake, BMW, Grossel, JH, Ketchak, Skane, Lufa, Kübeş, SHA-White, SIMD, and Echo. As you can see, these are all algorithms from the SHA-3 competition. So people thought that designers cannot build a good ASIC for these 11 algorithms, which run in consecutively, but actually ASICs were built for X11. So in order to make it more complicated, people added more algorithms like Hamsi and Fugue in X13. But as far as I know, there are also ASICs for X13. So we increased the number of algorithms in X15. Then we turn into X16, where you add all of these 15 algorithms, but also use SHA-512. So since it will be harder for ASICs, then people realized that instead of fixing the, the order that we use these algorithms, let's randomize it. So in X16R, these 16 algorithms are used, but in a random order. So whenever a new block is created, the mining puzzle actually determines in which order these 16 algorithms will be used for mining for the following round, so the following block. So this randomization actually makes it a lot harder to build a dedicated hardware. There's also another algorithm called X17, and it uses these algorithms. So these are important if you are interested in, writing mining algorithms for GPUs and so on. All right, let's go back to SHA3, the Keccak. So Keccak, the winner of SHA3 competition, is designed by Bertoni, John Damon, Feeters, and Gilvan A. So as you can see, John Damon was also the designer of AES, Advanced Encryption Standard. So there was a belief that if your John Damon is in your team, then you win the competition. But in the NIST lightweight competition, which actually the winner announced in February 2023, the winner was Ascon and John Damon was not in the team. So, this myth was also destroyed. As you can see, it has the same message digest length as SHA2 because we wanted to have this as a replacement. Whenever we want, we could, move from SHA2 to SHA3. So simply change the algorithm, and since the message digest length will be the same in your databases, you didn't need to make much modifications and so on. So block size actually depends on the message digest length. Number of runs also depends on the message digest length. But this time, it is not Merkle-Damgard construction, it is a sponge construction. And this algorithm used in the proof of work algorithm, in other words, Ethereum mining. The algorithm in Ethereum mining is referred to as ET hash. So Ethereum uses Keccak, but it should be noted that it is slightly different than the standardized version of Keccak, namely SHA3. Because a late change in the standardization process of SHA3 resulted in a different padding than the one used in ET hash. Thus, sometimes the used hash algorithms in ET hash are referred to as Keccak 256 instead of SHA3 256, or Keccak 512 instead of SHA3 512. So in the proof of work algorithm of Ethereum, instead of SHA-256, Ethereum uses Keccak. When you compare Bitcoin with Ethereum, this is the main difference between their mining algorithm. Of course, this definition no longer valid because in September 2022, Ethereum moved from proof of work to proof of stake. So miners no longer using these algorithms to mine Ethereum. Instead, we are, have delegators and so on in the proof of stake to determine which block to be written in the blockchain. Recall that this sponge function construction was something like this. So this SHA3 actually is fed here in this F, and you produce the hash. But of course, question is what the SHA3 here looks like. So I will show it with pictures instead of giving the mathematical formulas because it has a huge state and it performs a lot of operations. So it is easier to visualize than, look at the mathematical definitions. So if we go back, I said that the block size here. So the internal state here is represented as a three-dimensional cube, rectangle. So we perform operations on different parts of this internal state. So we have different definitions. For instance, the blue one is row and red one is this column. If you look at the two-dimensional slices, it is called slice. And in the Z coordinate, if you look at this part, it is called lane. So different operations are performed on these different parts. So first you apply Keccak key function to all of these rows, by the way. So you take a single row and perform these logical operations like NOT, AND, and XOR. And the result is written where it is taken from. Okay, so you apply it to every row in this picture. Then you apply the Keccak P function. So now you take a slice and you actually perform rotation, let's say. So you switch places of these values. Then you perform Keccak row function. This time it is on the Z coordinate. You apply it on the lane. Then also you apply the Keccak theta function, and it affects 2 or 3 columns. And the mathematical formula is here. So this is important because, as you can see, the definition is somewhat different and it is hard to implement this. And I tried to implement SHA3 years ago. I realized that I had I did a lot of implementation errors, and finally I had a working one. So if you are not using the reference implementation of SHA3, it's hard to implement correctly. And it turned out that even in the NIST reference implementation, there was a bug, and you could find collisions due to memory buffer overflow, which is a paper published just a few weeks ago, explains how you could do it. So this reference implementation is also updated a few weeks ago. If you are using the reference implementation and didn't know that, just update your implementation. But if you go back, I told you that there is a f function here that is applied to this internal state, right? That internal state after the f function actually turns into these values. So this is your internal state. You apply key function, p function, row function, and theta function. And you do this 64 many times, okay? As you can see, compared to Merkle-Damgard construction, this is somewhat different. But again, implementing it from the documentation was hard for me, and even it turns out that it was hard for the designers because there was a bug in the reference implementation. Again, NIST published a paper a few weeks ago. You can find it at ePrint, which explains how you can obtain a collision due to memory overflow. But they also show you how you fix that problem and so on.